Thank you very much. I want to talk about gunmetal solar cells, but this is only on the end. Asked what my main message is, actually, is that we are doomed. This is not a joke anymore. It's what I'm deeply believing already since I was very young. Looking at our world, I thought this will not continue forever. And I really think that we are as much threatened as these three guys, which, no, it's more than three, no, it's three. This is a view graph I'm using since 25 years already. So you can see that I'm preaching this already quite some long time. And if I really look at what has happened, what are the consequences, not only of me telling this story, you find quite a few people telling you this. It's a very nice TED talk, actually, with the main message, I don't think we are going to make it. There are quite a few pessimists out there, like me. And maybe the secret message of this talk is that you can be pessimist or realist and still do things. So why are we doomed? We are doomed because we forget that there is a real world outside. Maybe we think too much about all the different worlds in our heads because we don't want to see that there is a real world outside, which is limited and which we have exceeded already. The ecological footprint, actually the result of a PhD thesis, so PhD students can have a very big impact, actually. Matthias Wackernagel wrote his PhD thesis on the ecological footprint, trying to describe how much nature we use actually in whatever we are doing. So the footprint analysis has become a very important way of analyzing the status of our activities in a limited world. And the result is what you can see here in terms of footprints of nations. So this is the ecological footprint by country per person. Everybody's contribution to using our environment for whatever we are doing. And this shows one bar for every country. So of course, those bars which are the longest are describing the activities of every person in a country. And if it's long, we are having a very large footprint. So looking at Estonia, we are aiming at world leadership here. Which is maybe no wonder, because this is a big country and very few people, but still, most of us live in a town. As you know, also in Estonia, most people live in urban areas, so it may be more than just the big area which leads to this. Actually, Germany and Austria and so on, those countries I'm living in also, have also a big footprint, but compared to Estonia, it's relatively small. It's nearly double as big in Estonia. Now, analyzing this footprint worldwide, so the main aim is telling you a little bit about what's going on in the world average, of course. You can see the different activities contributing to this footprint, and you can see that the blue area is by far the largest contribution. This is energy. This is the carbon footprint. This is connected with burning fossil fuels, releasing the CO2 into the atmosphere. And then, of course, you need some world which takes up all this carbon dioxide. And the world should be already 1.5 worlds, as you see in total. Okay, so this one world we are having is already too small for all of us. Now, this is why I started to work on energy. And in energy, of course, later than the footprint came the discussion about climate change. So we all know that the temperatures are rising. You can see here the latest data on this temperature rise, which has reached about a degree Celsius. Okay, and this degree Celsius can be seen in its context only if you compare it with the last 1,000 years on the left, and you can see that we have exceeded whatever maximum levels existed in the last 1,000 years. Now, talking about the reason for this, of course, we have to analyze temperatures and CO2. So this shows temperature and CO2 and methane data actually during the last 500,000 years. So this is much more than human history. Human history starts about here, about 150,000 years ago with Homo sapiens. And this last part, when by some reasons which are not really understood fully, the variations actually have been extremely small. This is the known history. This is what we really know about our environment and about mankind. And it has been a very constant temperature and CO2 time. This is when culture developed. So culture maybe have come into existence because of this constant environmental conditions and our possibility to develop luxury like culture. If we look at the last 500,000 years, the CO2 level have always been between 200 and 300 ppm. This is the unit in which we measure the concentration of CO2 in the atmosphere. And now, since some time, we are able to measure this. Most famous are the data on the top left from Mauna Loa, where CO2 levels are directly measured, but you have meanwhile different measurement stations, including the South Pole and so on, Antarctica, and you see the CO2 levels, of course, rise everywhere in the world. Now, putting these data together, the last 500,000 years and the last 100 years or 70 years, then you can see what is really happening. From these 200 to 300 ppm, we have gone already to 392 ppm. This is the latest record data. And you can see that this is rising. And one question is, where will it go? What will be really the CO2 level we have to deal with? Will this be 550, 750, 1,000 ppm? For some time, quite some time, this has been unknown. There's a new science paper, and the conclusions you can see here. This came out this year, analyzing what will be the consequence of just continuing what we have done all the time, business as usual. And you can see it says, if we continue with burning fossil fuels, the CO2 level will rise to 900 to 1,100 ppm, at least. This already by the end of this century, which means that the temperatures will rise by 5 to 10 degrees, in polar regions even between up to 15 to 20 degrees. So we are not talking about point-something degrees anymore. We have to talk about 5 to 10 degrees, which is, if you think about the consequences, which is a catastrophe for our nature. There can be no doubt about it. It's a climate state, as the paper says, never before experienced in our evolutionary history, not to talk about mankind's history, as I've shown. Now, the impact of energy has been analyzed actually in a very interesting paper which came out from the IPCC work. The International Panel on Climate Change is this international organization of climatologists trying to predict and analyze the future, published in 1992, 20 years ago, published then in Nature a few years later in 1998, the energy applications of future atmospheric stabilization of CO2 content. And this basically shows these three curves, which the increase in energy need of the world is analyzed. Of course, the energy we consume worldwide depends on the number of people we are. So the first curve is actually the population growth, and this is shown on a logarithmic scale. And a linear behavior on a logarithmic scale already means an exponential growth. You can see these data, which consists of two halves actually. In the middle is this dashed line. This is when this analysis was done, 1990. Okay? So all the data to the left was what was available to the scientists, and all the data on the right of this dashed line are the predictions or assumptions for the future. And as you can see, people tried just to continue this curve of the past somehow into the future with some assumptions. In population growth, they assumed that right at this point when they analyzed, there will be a turning point in this curve, and instead of an ever-increasing exponential growth, population would stabilize and maybe reach a limiting level of about 10 billion people on Earth or something. But actually, looking at the real data, there's not much evidence that this is really happening, so today's data are already above this curve. Consequence, the first curve of the assumption is already optimistic. The second curve shows how much these people consume. So it tries to measure our activities per person. Okay, it's measured in gross domestic product. We will hear more about measuring wealth, and we will learn that gross domestic product is one of the worst numbers to describe wealth. However, for energy consumption, this is still a useful value. And you see, the assumption is that this need per person will increase with 1.6% per year. Looking at the real data, you can see this is the 2010 data. This is far too optimistic. And what has been estimated actually for the future is a steady growth by 3.2%, even starting from this today's 10.7 unit, which we have here. The last one is then energy saving. So indeed, since some time, you can see there is a declining curve. This shows that the same amount of goods are produced with less energy. This is energy saving, of course. And what you can see is that it's assumed that this will decrease further with 1% per year slope, which of course means that in 50 years, you will be able to produce the same amount of goods with half the energy, right? That's the idea. And the total energy consumption is just the product of these three curves. As I said, first curve being already optimistic, second curve being much too optimistic, and then it really doesn't matter too much what you assume for the third curve. The product will be a rising curve. And just to give you an idea about the units we are consuming, this is the power consumption I want to talk about. And the power consumption of a laptop is in the order of 1 watt, a toaster of a kilowatt about, a small airplane is a megawatt, so always a factor of 1,000. Then a big power plant is 1 gigawatt, and if we talk about world energy consumption or power consumption, actually we are in the order of terawatts. So I talk about terawatts, and this shows the result of this analysis. The energy consumption, the power needed, will increase and will reach around 30 terawatts in 2050. When the analysis was done, we had about 11 terawatts. In 2005, we had about 16 terawatts. So it's quite still relatively realistic value. What you see in these curves also are black curves. And this shows how much of this energy can be produced by releasing CO2 if we want to keep the CO2 levels below a certain value. So you see the lowest curve, 350, shows how much CO2 can be released by energy production if we want to stabilize our CO2 concentration around 350 ppm, and the uppermost curve is actually 750 ppm. Above this, there is not even stabilization. The CO2 values will just continue to increase and go through the ceiling. Okay, so no limit can be found in these calculations if we have larger CO2 emission than given by these curves, which of course means in 2050, for a stabilization of CO2 levels on these, say, 1,000 ppm, which has now been predicted meanwhile, we need to produce at least 12 terawatts of energy CO2 free. This is the absolute minimum which is required. Otherwise, our climate will completely collapse. Okay? So at least 12 terawatts. If we want to stabilize it on values which are close to what we had in the past, all 30 terawatts will have to be produced CO2 free. That's the aim. Okay? So everybody who works on energy, on sustainable energy production, must have the aim to produce in 2050 between 10 or 20, better 30 terawatts. This shows how much actually if you want to reach certain level. So for 350 ppm, actually 32 terawatts of CO2-free energy will be required. Between 10 and 30, that's the aim we have. Everybody working on this. This actually shows growth rates of renewables. Of course, only renewables are able to do this, and I could now start discussing all the different approaches. I can also discuss about nuclear energy. Let's just assume we have 10 terawatt of nuclear power installed, really, which would require one new atomic power plant every day until 2050. Okay, this is just giving you an idea about the amounts I'm really talking about. These 10 terawatts of nuclear power would consume all known uranium reserves, in 1 year. That's the amount of uranium we have available. So just forget about nuclear energy, okay? For saving our world, there will be no contribution by nuclear energy. This is for sure. But also the other renewables have a serious problem to reach values of about 10 to 30 terawatts. And basically what remains is wind and photovoltaics, which actually had already during the last year's growth rates of larger than 25 to 30% per year, because that's the growth rate we must reach to really achieve amounts of these 30 terawatts in 2050. So in principle, photovoltaics and wind can solve the problem, but they have to continue to grow with the same speed as they have been growing, fortunately, during the last few years. This would be the area required by photovoltaics or solar plants, could also be solar thermal power plants actually, to provide 20 terawatts. So you can see, in principle, it's not a problem. We have enough area available, we have enough sunshine, we heard already the huge amount of sunlight we have available, so it could be done. But, of course, it has to be cheap enough, and actually the only consequence is that we need cheap sources. This shows this growth and the price connected with it in more detail. So extrapolating the curve, you could see you come in orders of magnitude which are interesting and possible. However, it has to be a very cheap technology, and this is actually where our work in Tallinn comes into play. In addition to the price, you have to take into account that you should use elements, components of your solar cell, which are available in large enough amounts. Some of these are produced in amounts which are far too low, and also the known resources are much too small to really be able to contribute to, say, just 1 terawatt production per year. just the comparison of the production in 2007, which in the case of indium, for example, is about 500 tons per year, with the 30,000 tons per year you would need, shows that your solar cell should not contain indium. So here comes the gunmetal into play. Gunmetal, this is actually what guns were made from in the Middle Ages. You know it's bronze. Our cannons, which we can see in Old Town, of course, still today, are made from bronze. And in order to make it harder, zinc was added. So gunmetal is an alloy of copper, zinc, and tin. Like the old Estonian crown coins, actually was an alloy from copper, zinc, and tin. And the solar cells we are making is copper, zinc, tin, sulfides or sulfur selenides, as you see. So this is the ultimate conversion I'm working on. One of my roots is actually the peace movement, so conversion of military things into civil things has always been a big issue for me. I was very happy to see that this might be the ultimate conversion. We make powders from these. We put these powders in layers, and we make solar cells from them. We have a very cheap production technology, which start with this powder production here in Tallinn. And then we developed a way of making modules from this, all in a way which we think can be cheap enough. This is the solution we can contribute. Of course, this is still small scale, but it could be a contribution Estonia actually brings for one of our key problems. Summarizing, key problem being 20 to 30 terawatts of energy. Otherwise, our climate will collapse completely. And we hope that there might be still some contribution at least. As I said in the beginning, I'm absolutely pessimistic that this is still in time, but what can we do? We have to try at least, and this is what we try at the moment. Thank you very much.